In lab, we have routinely measured DC voltage and current. What do you suppose you measure if either of the circle buttons, the AC voltage button and the AC current button, are engaged? This video is devoted to uncovering the notion of the effective value of a periodic waveform. The effective value is also known as the root mean square value, as we shall see. The AC voltage and current measurements on a digital multimeter display the effective value of the waveform being probed. We will begin this video by reviewing the concept of average power by considering two sets of example waveforms. We will then argue what the effective value is when the periodic waveform is sinusoidal. Effective value is pertinent to all periodic waveforms, and thus we will give the general formula that one can use to find the effective value of a given voltage or current waveform. We will conclude with a very simple example that relates a sinusoidal waveform to an effective DC value and consider examples from the lab for you to interpret. The figure on this slide shows hypothetical voltage and current waveforms for a resistor. As the equations at the bottom of the slide suggest, the amplitude of the voltage waveform is 5 volts and the amplitude of the current waveform is 2 amps. The frequency is 1000 hertz. A key item to notice, and one that we have found in previous videos, is that for a resistor, current and voltage are in phase. We will take these two waveforms and multiply them together to find the instantaneous power. Before we do that, however, let's consider voltage and current waveforms for an inductor. On this slide, we show hypothetical voltage and current waveforms for an inductor. The amplitudes of the waveforms as well as the frequency were chosen to be the same as in the case of the resistor. What is the key difference in the case of the inductor? For an inductor, voltage leads current by 90 degrees. While we could take up the case of the capacitor as well, comparing the instantaneous power associated with a resistor and an inductor will be sufficient to remind ourselves of a key observation from a previous video. On this slide, I show a plot of the instantaneous power as a function of time for both the resistor and the inductor. Remember that instantaneous power is simply the product of the voltage and current waveforms. I have used the expressions for the voltage and current from the previous slides. What I would like you to do is attempt to identify the waveforms, which corresponds to the resistor and which to the inductor. As a hint, think average value. Notice that the average value of the red waveform is 0. So again, here's the 0 axis here. We know that below and above for the red waveforms, they have equal area, and so the integration will result in 0. So again, recall that average power is just that. It's found by integrating the instantaneous power over a period and dividing by the period. Therefore, the red waveform describes an element in which there is 0 average power. The blue waveform, on the other hand, clearly describes an element that has a non-zero average power. Therefore, the blue waveform describes the resistor and the red waveform the inductor. On the next slide, we'll see how this relates to effective value. Recall from the video on instantaneous and average power that the average power when dealing with sinusoidal signals is given by Vm Im over 2 times cosine of the difference of theta v and theta I. Our goal now is to find the value of the DC voltage and current. We'll call these V effective and I effective that yield the same average power delivered to a resistor as that from a sinusoidal input. The key words here are average power and resistor. It would not make sense to speak of average power associated with a purely reactive element, as we know that ideal inductors and capacitors dissipate 0 average power. How do we take the equation on the top of the slide and make it pertain to a pure resistor? In its present form, it can be used to evaluate the average power associated with any impedance, including a composite impedance consisting of both real and imaginary components. As we just saw, voltage and current are in phase for a resistor, and thus theta V minus theta I equals 0, and cosine of 0 is 1. Therefore, for a pure resistor, the average power equation becomes simply Vm Im over 2. Recall that Vm and Im correspond to peak amplitudes of the sinusoids. To find the effective values of voltage and current, we equate the average power equation to the power dissipated by a resistor with DC voltage and current. That is as follows. Vm Im over 2, again, corresponds to the AC case. And recall, V effective and I effective represent DC voltages. Given this equation, in terms of their peak amplitudes, what are the effective values of the sinusoidal voltage and current waveforms? Clearly, V effective equals Vm over root 2, and similarly, I effective equals Im over root 2. While we found the effective values of sinusoidal waveforms based on a simple argument from a previous result, let's look briefly at the generalized formula for finding the effective value given a periodic waveform. Remember what we're doing. We're attempting to find the equivalent DC voltage or current which yields the same average power as does the periodic waveform. A comparison of the circuit shown will help us derive the general result. Recall that the average value is found by integrating the instantaneous power over a period and dividing by the period. In the case of the circuit on the left, the instantaneous power is simply I of t squared times R. The average power for the circuit on the right is simply I effective squared times R. On the next slide, we solve for I effective. Here again is the equation with which we left off. We can solve for I effective, leaving us with the following. How do we interpret this result? Notice the first thing we do. We square the expression for the time domain waveform. We then take the mean value of the square. Finally, we take the square root of the mean value of the square. What is another name then for effective value? It's root mean square, abbreviated RMS. I recommend that you try to confirm our earlier result for the sinusoid using this general formula. The process is really very similar to what we did in the video in which we found average power from instantaneous power. By the way, the derivation is shown in the course notes. As a quick means to help solidify our understanding, let's consider the following very simple example. Let's assume that we have a 100 ohm resistor with a 10 volt drop across it as shown. What is the average power dissipated in the resistor? Pause the video and make that quick calculation. V squared over R yields a convenient 1 watt of power in this case. Okay. Let's now imagine that instead of a DC voltage across the 100 ohm resistor, there's actually a sinusoidal voltage. What is the peak amplitude of the sinusoidal waveform such that 1 watt of average power is dissipated in the resistor? Again, pause the video and make this calculation. I hope it makes sense that the amplitude of the sinusoidal waveform will be larger than 10 volts. In this case, the peak amplitude of the voltage waveform must be approximately 14.14 volts. So what we're doing is we're solving for the amplitude V sub m, and we know what VRMS is, right? It's the effective DC voltage. We started with a DC voltage of 10 volts. Solving for V sub m, we find 14.14 volts. So in other words, the voltage signal would be given as follows, 14.14 times cosine of omega t, for instance. All right, let's close with 3 examples from the lab for you to reason out. On the next slide, you'll see a brief video, and it'll show a function generator, digital multimeter, and an oscilloscope. The DMM will be set to measure AC voltage, that is, the effective value of the waveform. The following 3 waveforms will be considered. A 1 kilohertz sinusoid with 3 volt peak amplitude. a 1 kilohertz square wave with, again, 3 volt peak amplitude. Finally, a 1 kilohertz triangular wave with 3 volt peak amplitude. We should know what to expect for the RMS value of the sinusoid. Simply the peak voltage divided by root 2. Before proceeding to the next slide, think for a little bit about the square wave and the triangular wave cases. Do we expect the effective value to be greater than that or less than that in the sinusoidal case? Well, there's a bit of math to figure out for the effective value of the triangular wave. See the course notes if you're interested. You should be able to figure out the RMS value of the square wave quite easily from the general formula on slide 7. Even though the formula is written in terms of current, it's equally valid for voltage when using V of t instead of I of t in the formula. Spend a minute on the square wave case, and when you think you have it figured out, watch the video and see if you have it right. Okay, here's the experimental setup. Obviously, here's the oscilloscope. Here is the digital multimeter set to measure AC voltage, and here is the waveform generator. Note it shows 6 volts peak to peak. This is a 6 volt peak to peak waveform. The 0 to peak is then 3 volts. Okay, so we have a 3 volt amplitude sine wave, and it looks like we have an effective value of 2.12. Does that make sense from what we've seen before? Okay, let's go ahead and watch the video. So again, we're starting out with the sinusoidal waveform, 3 volt amplitude, RMS of about 2.12 volts. We switch to a square wave with a 3 volt amplitude, 6 volts peak to peak, but 0 to 3. That's giving us an RMS of 3 volts. Let's trigger on the triangular wave. Again, a 3 volt amplitude. In this case, the effective value is about 1.73 volts. Most decent digital multimeters do a reasonable job of determining the RMS values of the waveforms that were shown. It turns out, however, that with pulse signals, particularly ones with small duty cycle and large peak voltages, not all meters actually do a good job, and one must be aware of the assumptions made in the measurement. One should also be aware of the frequency limitations of the digital multimeter one is using, as this can significantly affect the accuracy of the RMS measurement. If you're interested, you'll find an application note regarding RMS measurements in the handout section of the course website.